So I want to start today by asking you, the listener, a question. And it's one of those questions that might just bend your brain a little bit.
Oh, I love these.
Right. So what if everything we know, and I mean absolutely everything about how life works, is just a localized bias?
Yeah, it's the ultimate reality check, isn't it?
It really is.
Because we look around our planet, we catalog millions of species, and we naturally assume, we've figured out the universal rules of biology. But, well, we are looking through an incredibly narrow keyhole.
Exactly.
We only know one single operating system for life.
Right, because we're so incredibly familiar with, like, the plants in our gardens, the pets in our homes, even the microbes that make our yogurt.
Yeah.
But what if we are just one tiny, highly specific chemical accident in a universe of completely different possibilities? So today, our mission on this deep dive is to shatter that localized bias.
I'm so ready for this.
We are going to explore this fascinating compilation of scientific articles, historical speculations, and various source materials on the wild, entirely plausible world of hypothetical types of biochemistry.
It's a journey that really forces us to define what life actually is, down to its fundamental physics, rather than, just relying on what life happens to look like on Earth.
Right. And to do that, we have to set the baseline first. For you, me, the tree outside, the bacteria in your gut Earth life relies on a very specific recipe.
A very strict recipe.
Yeah. We use carbon for our physical structure. We use water as the liquid solvent to move things around. And we use DNA and RNA to store and pass on information. That's it. That's the entire terrestrial playbook.
And because that recipe is ubiquitous here, it created what the late astronomer Carl Sagan famously called carbon chauvinism.
Carbon chauvinism. I love that term.
It's so good. He also coined water chauvinism, actually. It's this deeply ingrained, almost arrogant scientific blind spot.
Like we just assume we're the standard.
Exactly. Humanity assumes that because carbon and water work so flawlessly for us, all life everywhere in the cosmos must absolutely rely on them.
Right.
Sagan argued back in the 1970s that, demanding all life mimic Earth life is just a massive failure of imagination.
Okay, let's unpack this.
Yeah.
Because if carbon, water, and DNA are just one single way to bake the biological cake, we have to acknowledge that scientists aren't just sitting around philosophizing about the alternatives anymore.
Oh, no, not at all.
Right. They are actively modeling, testing, and in some terrifying cases, actually trying to create entirely alternative forms of life in the lab.
Which is wild.
We are moving out of science fiction and stepping into hard, rigorous, synthetic biology.
Yeah, the transition from theory to physical laboratory practice is really where this field has completely exploded. I mean, we are no longer just looking through telescopes, we are running the chemistry.
But before we even start looking out into the stars, we have to ask a much more unsettling question.
Oh, I know where you're going with this.
Yeah. What if alien life is already here? What if it's hiding right here on Earth, sharing our environment, and we just can't see it? So let's talk about the concept of the shadow biosphere.
Right. So the shadow biosphere is a hypothetical microbial ecosystem right here on our planet that uses radically different biochemical and molecular processes than currently known life.
Okay.
We're talking about microscopic organisms that might have originated from a completely separate second genesis event on early Earth.
Wow. But when you say shadow, it almost sounds, I don't know, ethereal, like ghosts.
Yeah, it does sound a bit sci-fi.
But we are talking about physical, living, metabolizing microbes, right?
If they are physical, why wouldn't we have found them by now?
Well, that's the big question.
I mean, if I scoop up a handful of dirt from my backyard, I can send it to a lab, run a genetic sequence on it, and see every microscopic thing living in that dirt.
Well, you can only find what your tools are specifically engineered to look for.
Right. When you scoop up that dirt and run it through a modern genetic sequencer, you're usually using a technique like PCR, polymerase chain reaction.
Right, which we all heard a lot about recently.
Exactly. And PCR relies on highly specific chemical primers. These primers are short strands of RNA or DNA designed to physically lock onto standard, familiar Earth DNA.
Got it.
They are chemically coded to find our standard carbon-water nucleic acid chemistry.
So if there's a microbe in that dirt that uses a completely different molecular architecture, the primer just what? It bumps into it and bounces off.
It bounces right off, literally. To our genetic sequencers, a microbe from a shadow biosphere wouldn't even register as biological. It would just look like a microscopic speck of inert dirt or just, background chemical noise.
That is wild.
We wouldn't sequence it because we wouldn't even know how to ask it to reveal its code. Scientists like Carol Cleland and Paul Davies have hypothesized that these shadow microbes could be hiding anywhere.
Like where?
They could be deep in the Earth's crust, thriving in the extreme heat of hydrothermal vents, or sealed away in ancient rocks, completely unnoticed by modern biology.
That is deeply unsettling. It's
Yeah.
like two people standing in the exact same room, shouting at the top of their lungs, but they are tuned to entirely different radio frequencies.
That's a perfect analogy. The sound waves just pass through each other.
So let's look at one of the most viable ways a shadow biosphere could exist right under our noses. It's a concept that sounds like it's straight out of Alice in Wonderland.
Oh, mirror life.
Yes. Alternative chirality or mirror life.
Right. So chirality is a foundational concept in chemistry regarding molecular handedness. The easiest way to visualize this is to literally just look at your own two hands.
Okay, looking at them.
Your left and right hands are mirror images of each other. They have the same number of fingers, the same structure, the same components, but you cannot perfectly superimpose your left hand face down on top of your right hand face down.
Right, the thumbs stick out in opposite directions.
Exactly. And molecules work the exact same way.
So you can have a complex carbon molecule and you can build an exact mirror image of it, structurally identical in its parts, but spatially flipped.
Precisely. And on Earth, for reasons we still don't fully comprehend, perhaps just a random chance early in our planetary history life, almost universally uses left-handed or L-form amino acids to build its proteins.
Okay.
And it universally uses right-handed or D-form sugars to build the backbone of its DNA and RNA.
It's as if every single life form on Earth, from a blue whale to a dandelion, just agreed to drive on the right side of the road.
Exactly.
But theoretically, designing cars to drive on the left side of the road works perfectly fine, too. The physics of driving don't change.
Right. A mirror image biochemistry, one that uses right-handed amino acids and left-handed sugars, is theoretically flawless.
Wow.
The chemical reactions, the thermodynamics, the folding of the proteins, it would all proceed in the exact same way. A mirror image cell would function perfectly, but it would be totally physically incompatible with us.
Because life relies on molecular recognition. Right. Molecules have to fit together like puzzle pieces.
Think of it like a lock and a key. An enzyme in your body is shaped perfectly to grab onto a specific left-handed molecule. If it bumps into a right-handed version of that exact same molecule, it can't grab it.
It just misses.
It's exactly like trying to shove your left hand into a right-handed baseball glove. It physically will not fit no matter how hard you push.
Okay, here's where it gets genuinely alarming. Because based on the source material, synthetic biologists aren't just theorizing about this anymore.
No, they are doing it.
The University of California, San Diego recently received a $4 million grant to actively try to boot up and create synthetic mirror image cells in the laboratory. They're trying to build a left-handed glove.
Like, technological leap required to do that is astounding, but it raises a vital, highly dangerous real-world implication.
Yeah, I bet.
If you create a fully functioning mirror image microbe, it would behave identically to its normal counterpart in a sterile petri dish. But if it got out into the real world, it would be completely invisible to the immune systems of every existing Earth organism.
Wait, let me make sure I'm fully grasping the mechanics of this. So if I get a paper cut and get infected by a standard everyday bacteria, my white blood cells deploy antibodies.
Right.
Those antibodies recognize the proteins on the surface of the bacteria, bind to them, and destroy the invader. But if I get infected by a mirror bacteria...
Your white blood cells are entirely constructed out of left-handed amino acids.
Oh, man.
So they would bump into the mirror microbe, try to grab onto its right-handed surface proteins, and just slide right off.
I couldn't grip it.
The physical locking mechanism wouldn't engage. The mirror microbe would be functionally invisible to your immune system. Furthermore, it would be immune to nearly all of our standard antibiotics.
Because they're chiral too.
Exactly. Penicillin, for example, works by jamming itself into the specific chiral structure of a bacterial cell wall. If the wall is mirrored, the penicillin just floats on by, totally useless.
So we are talking about a completely unstoppable pathogen.
Basically, yes.
There is some intense reporting on this. The sources mentioned Carl Zimmer covering this in the New York Times recently, in late 2024, detailing severe warnings from the scientific community against creating a second tree of life.
Yes.
And there was a major technical report from Stanford researchers, alongside a corresponding paper in Science magazine, that explicitly confronted the existential risks of mere life escaping a lab. It could wreak absolute havoc.
The concern is incredibly valid. A synthetic shadow biosphere could operate without any natural predators. It could outcompete natural biology for basic resources, or, as you mentioned, cause unstoppable diseases because the standard biological defense mechanisms simply wouldn't recognize it as a threat.
But I have to push back on the natural shadow biosphere idea for a second.
Sure.
If a naturally occurring mirror-life biosphere already exists on Earth, maybe deep underground, why hasn't it devoured our biosphere by now?
That's a fair
Or
question.
why haven't we accidentally destroyed it? Is it really just that radio frequency analogy where we are completely unable to interact?
Well, it largely comes down to that inability to interact chemically. A mirror microbe couldn't digest standard Earth proteins, and we couldn't digest it.
We just pass right through each other.
We would just pass through each other's digestive tracts intact, yeah. But we shouldn't view stereochemistry as a completely rigid, unbreakable law across every single domain of life.
Oh, so nature does occasionally bend its own rules.
It does. For example, certain ancient basal organisms, like those in the domain Archaea, sometimes utilize alternative enantiomers, different chiral forms in their cell walls compared to the bacteria or eukaryotes we are more familiar with.
Wow, okay.
There are even specific bacteria that utilize diamino acids to toughen their cell walls against antibiotics, so nature plays with chirality at the margins.
But a whole inverted ecosystem.
Right, a completely inverted, independent ecosystem. It would likely just coexist in parallel. It might metabolize raw, inorganic resources like deep-sea thermal energy or basic minerals without ever needing to chemically interact with our biological matter.
So that's flipping the molecules around like a mirror. But what if we go deeper?
Oh, let's do it.
What if we fundamentally change the building blocks themselves? Because if chirality is just flipping the existing hardware, what happens when we start actively tinkering with the actual hardware of genetics?
Then we step into the realm of alternative nucleic acids. To understand this, we really have to look at the architecture of Earth life's information storage, which is DNA and RNA.
Right.
They are composed of a backbone made of alternating sugar and phosphate molecules. And attached to this backbone are the nucleobases, the famous genetic letters A, T, C, and G.
We've all seen the double helix model. The sugar and phosphate are the twisting handrails of the spiral staircase, and the A, T, C, and G bases are the steps connecting the handrails.
That structural framework is universally true for us. But chemically speaking, there is no fundamental law of physics that dictates you must use ribose or deoxyribose sugars for those handrails.
Really?
Scientists have successfully developed entirely artificial backbones, creating what we call xenonucleic acids, or XNA.
And based on the notes, there are some incredibly wild variations of this.
Oh, absolutely.
You can swap out the sugar completely. There's TNA, which uses a different sugar called 3-Os. There's GNA, which uses glycol. And then there's PNA, peptide nucleic acid.
PNA is fascinating.
That one blows my mind because it gets rid of the sugar and phosphate entirely and replaces the handrail with peptide bonds, which is the exact same chemical bond that links amino acids together to form proteins.
Right. PNA is just a brilliant piece of biochemical engineering. By using a peptide backbone, PNA actually forms a stronger, more stable molecule than standard DNA.
How does that work?
Well, the lack of electrical charge on the peptide backbone means the two strands of the helix don't repel each other as strongly as DNA strands do.
Oh, that makes sense.
Yeah, these XNAs can still store genetic information perfectly, and they can even be made to evolve in a lab setting, but they are chemically distinct. And crucially, because they are completely artificial, the natural enzymes in our environment that normally chew up and degrade straight DNA, they don't even recognize XNA.
So if you built a microbe with a PNA backbone, it would have incredibly durable genetics.
Very durable.
So XNA changes the handrails of the genetic staircase.
Mm.
But what about the steps themselves? What about the A, T, C, and G? That brings us to Hachimoji DNA.
Hachimoji. It literally translates from Japanese as 8 letters.
8 letters, wow.
In 2019, a team of researchers funded by NASA successfully expanded the genetic alphabet. Instead of relying on just the standard four letters, they engineered and integrated four entirely new synthetic nucleobases, which they named P, Z, B, and S.
I want to make sure we conceptualize how massive a change this is, because upgrading to Hachimoji DNA isn't just like dropping a few new vowels into an English dictionary.
Not at all.
Because genetic code is read in pairs, it's closer to upgrading a computer's foundational code. Like, imagine a computer running on standard binary code, ones and zeros. The entire digital world is built on that. Hachimoji DNA is like upgrading that computer to run on zeros, ones, twos, threes, fours, and fives simultaneously. It exponentially increases the density of information you can store in the exact same physical space.
The information density just skyrockets, and the fact that we can synthesize this in a lab raises a profound evolutionary question about how our own standard four-letter code came to be.
Yeah, why those four?
Exactly. Why did nature settle on A, T, C, and G, and why did it settle on the specific 20 amino acids we use to build our bodies? This leads us into a fascinating concept known as the alanine world hypothesis.
This suggests that the genetic code we have today wasn't always this complex, right? It didn't start out with 20 amino acids. It started with just four: alanine, glycine, proline, and ornithine.
Right, because evolution is an iterative process. Early life almost certainly had to be much simpler. From a purely chemical standpoint, a vast majority of the complex modern amino acids can be viewed as complex derivatives of alanine. Alanine is a structurally simple, robust amino acid that is highly efficient at forming the core secondary structures of proteins.
When you say secondary structures, you mean the literal shapes the proteins fold into.
Yes, exactly. Proteins aren't just straight lines. They fold into complex 3D shapes to do their jobs. Alanine is fantastic at building things like alpha helices, which look like tiny coiled springs, and beta sheets, which are flat, rigid, accordion-like structures.
Right, the building blocks.
These shapes are the foundational building blocks of all cellular machinery. The alanine world hypothesis suggests early life leaned heavily on alanine because it was readily available and structurally versatile.
But this invites a crazy thought experiment from the sources. What if evolutionary history had taken a slight left turn 3.5 billion years ago?
This is where it gets fun.
What if, instead of an alanine world, the chaotic primordial soup of early Earth had settled heavily on a proline world, or a glycine world as its foundation?
That slight deviation at the genesis of life would cascade into unimaginable biological differences.
Really, just from swapping the base amino acid.
Oh, absolutely. Proline, for instance, has a very unique, rigid cyclic structure. It creates literal kinks or sharp turns in a protein chain.
Okay.
If the earliest genetic code had based its entire architecture on a proline-heavy chemical scaffold, the resulting protein-like polymers, which chemists call foldimers, they would fold and behave in fundamentally completely different geometric ways.
So you would end up with cellular machinery that moves and flexes in ways Earth biology simply cannot replicate.
The downstream implications are staggering. Because the microscopic proteins fold differently, the macroscopic tissues they build would assemble differently. It would result in morphologically radically different body plans.
Wow.
The creatures that would evolve in a proline world would look physically alien to us. The fundamental architectural tension and flexibility of their tissues, their muscles, their very cellular structures would be built on an alien geometric foundation.
We would literally have a parallel biological reality just based on which amino acid happened to win the chemical lottery in a warm puddle 4 billion years ago.
It's humbling.
It really shows how deeply contingent and fragile our specific version of life really is. So, okay, we've messed with the genetic code, we've swapped out the handrails, we've added new steps to the staircase. Let's tackle the ultimate science fiction trope.
I'm Ray.
What if we swap out the primary structural element of life itself? Let's talk about carbon and its most famous, legendary rival, silicon.
Silicon-based life. It is the absolute darling of science fiction. From the rock-eating Horta in Star Trek to countless other alien species in literature. And chemically speaking, there is a very rigorous logical reason why both writers and astrobiologists gravitate toward it.
Yeah, if you look at a standard periodic table of elements, silicon sits directly beneath carbon in the exact same column.
Right.
That column placement means it's tetravalent. It has 4 electrons in its outer shell available for bonding, meaning it can form 4 chemical bonds with other atoms simultaneously, exactly like carbon.
Exactly like carbon.
That unique ability to form 4 bonds at once is the superpower that allows carbon to create such massive, complex, diverse chaining molecules. The very molecules required for life.
Mm-hmm.
So the logic follows.
Mm-hmm.
Why wouldn't silicon be able to do the exact same thing?
The logic is sound at a glance, but the harsh physical realities of atomic structure present massive hurdles for silicon. Just because two elements share a column doesn't mean they behave identically.
Why not?
We have to look at the physical size of the atoms. Silicon is a significantly heavier and physically larger atom than carbon.
So its electron cloud is pushed further out from the nucleus. Why does being larger make it worse at building life?
Because distance weakens the force of the bond. When silicon shares electrons with another atom to form a covalent bond, that shared electron pair is sitting further away from the positively charged nucleus.
Oh, I see.
Because it's further away, the electromagnetic attraction is weaker. The covalent bonds silicon forms are physically longer and substantially weaker than carbon bonds.
So it's like trying to build a massive, intricate Lego castle, but your Lego bricks are just a little bit too large, and the interlocking snaps are weak and loose. The higher you build the castle, the more it just wants to sag and fall apart.
That is an excellent way to visualize it. Carbon's smaller size allows it to hold its atoms close and tight. This allows carbon to easily form stable double bonds and even triple bonds with itself.
Which are important.
Oh, double and triple bonds are absolutely vital for creating the diverse complexity of organic chemistry. They lock molecules into rigid shapes. Silicon really struggles to do that.
Yep.
Multiple bonds between silicon atoms are highly unstable and prone to breaking.
Yikes.
Furthermore, if you look at silanes, which are the silicon equivalents of carbon-based alkanes like methane, ethane, or propane, their real-world behavior is violently fragile.
They don't just fall apart quietly, do they?
No, they do not. Silanes react explosively with oxygen, and if you put long-chain silanes into water, they rapidly and aggressively decompose. The water molecules just rip the weak silicon bonds to shreds.
Which means a water-based planet like Earth is basically a death zone for complex silicon chemistry.
Absolutely.
There's also a brutal statistical reality for the silicon dreamers in the sources. Carbon is roughly 10 times more cosmically abundant than silicon in the universe.
Yeah, that's a big factor.
Astronomers who study the interstellar medium, the gas and dust between the stars, they use spectroscopy to identify molecules floating in deep space. They have currently cataloged 84 different complex molecules containing carbon. How many have they found for silicon?
It's pretty low, right?
Exactly 8. And here's the real kicker.
Yeah.
Half of those 8 silicon molecules also include carbon.
Nature just has a staggering, quantifiable preference for carbon in the cosmos. It is abundant, it is stable, and it forms complex shapes easily. But, we shouldn't dismiss silicon entirely based on Earth-centric physics.
Really?
It just requires a radically different environment to thrive. Where carbon struggles and freezes, silicon might actually excel.
Okay, so if a warm water ocean destroys silanes, where could silicon survive?
We have to look at extreme cold. The weak bonds in silicon compounds become a catastrophic liability at room temperature, but they might actually be a profound advantage at cryogenic temperatures.
Oh, wow.
Think of a world with oceans of liquid nitrogen sitting at nearly minus 200 degrees Celsius. At that temperature, carbon-based organic chemistry would freeze completely solid.
We would just stop.
Exactly. The molecules would lose all kinetic energy, they would be too rigid to interact, and life would simply halt.
But because silicon bonds are weaker and looser?
Exactly. At those ultra-low temperatures, silicon molecules might retain just enough flexibility and instability to remain chemically reactive. Polysilienols, which are essentially silicon's version of carbon-based sugars, are remarkably soluble in liquid nitrogen.
That's crazy.
So a freezing liquid nitrogen ocean on a rogue planet floating in deep space could theoretically be a bustling hub of silicon biochemistry.
So freezing cold is one option. What about extreme heat?
For that, we look to silicones. Now, pure silicon chains are fragile, but silicones, which are polymers built out of alternating silicon and oxygen atoms, are incredibly tough.
Like silicone spatulas and baking bats.
Exactly. The silicon-oxygen bond is phenomenally strong. Silicones might survive beautifully in highly acidic, blisteringly high-temperature environments.
Okay.
Imagine a planet entirely covered in boiling sulfuric acid. Standard hydrocarbons would be instantly dissolved and destroyed, but a silicone-based biochemistry might thrive in that exact environment.
I love how astrobiology forces us to reframe environments. Earth is a paradise for us, but to a silicone organism, Earth is a freezing, watery hellscape that would just dissolve it.
It's all relative.
But I want to challenge this with a very local Earth-centric argument. The Earth's crust is overwhelmingly made of silicate rocks. By mass, our crust is roughly 925 times more abundant in silicon than it is in carbon.
That's true.
We are quite literally standing on a giant ball of silicon. If silicon life was ever going to spontaneously spark into existence anywhere, shouldn't it have happened right here in our own crust over the last 4 billion years?
That is a phenomenal point, and it perfectly sets up one of the most intriguing and unorthodox hypotheses regarding the very origin of life on Earth. The chemist A.G. Karen Smith proposed a theory where silicon did play a foundational role in the genesis of life, but not as the final product. It's known as the clay hypothesis.
Clay, like the mud you use for pottery, because that is made of silicate minerals.
Yes, exactly. Karen Smith argued that the very first self-replicating entities on early Earth weren't RNA or DNA. They were complex silicate crystals growing in ancient waters.
Wait, crystals?
Yeah. As these crystals grew, they formed specific structural geometric patterns. When the crystals fractured, those pieces acted as seeds that passed on that specific structural pattern as they continued to grow. It was a crude, purely mineral form of reproduction and information transfer.
Okay, reproducing rocks.
Yeah.
But how does that get us to carbon-based life?
The silicate mineral surfaces acted as a microscopic scaffold. The microscopic grooves and charges on the surface of the clay crystals attracted simple biogenic carbon compounds floating in the water.
Oh, I see.
The carbon molecules locked into the grooves of the silicon crystal, forcing the carbon to organize into more and more complex chains. The silicon provided the mold, the physical scaffolding.
Wow.
Over millions of years, as the carbon chemistry became complex enough to begin self-replicating on its own, eventually forming RNA, it essentially took over, outcompeted the minerals, and entirely abandoned the silicon scaffolding that birthed it.
That is profound. Carbon life used silicon as a stepping stone, a microscopic ladder, and then kicked the ladder away once it could replicate on its own.
That's a great way to put it.
And speaking of merging carbon and silicon, we don't have to look back 4 billion years. We just have to look at modern synthetic biology. A few years ago, researchers used a process called directed evolution, which is basically forcing rapid artificial selection in the lab to engineer a living protein. They took a cytochrome C protein from a naturally occurring marine bacterium, mutated it, and coaxed it to catalyze entirely new carbon-silicon bonds that do not exist anywhere in the natural biological world.
It was a monumental breakthrough in biochemistry. By forcing a living biological enzyme to efficiently bond carbon to silicon, they proved that biological systems can be artificially coerced into manipulating silicon. It completely blurs the rigid line we've drawn between organic biology and inorganic chemistry.
Before we move on from the weird elements on the periodic table, there are a few other wildly exotic possibilities that researchers have modeled. Borane-based life, for instance.
Boranes, yeah.
Boron is cosmically rare, and if you expose boranes to Earth's oxygen-rich atmosphere, they literally spontaneously explode. But in a highly reducing atmosphere like a planet with plenty of hydrogen but absolutely zero oxygen, boranes share an incredible amount of structural properties with hydrocarbons. They can form complex, stable networks.
And then you have the concept of metal oxide life. We tend to think of metals as rigid and inorganic, but metals like titanium, aluminum, and iron are incredibly abundant in the universe.
Right.
At Glasgow University, the Cronin group managed an incredible feat. They coaxed complex metal molecules called tungsten polyoxymetallates to spontaneously self-assemble into microscopic, hollow, cell-like spheres.
Tungsten. We're talking about microscopic bubbles made out of the exact same heavy metal we used to put in incandescent light bulb filament.
Literally, yes.
And these spheres naturally acquire porous holes that act almost exactly like the semi-permeable cell membranes of our own biology. It is mind-blowing how matter wants to organize itself.
It really is.
But okay, we need to ground this back in reality.
Okay.
Because all this talk of lab-engineered proteins and tungsten cells brings us to a very real, very public scientific controversy that actually happened.
Oh, I know this one.
A few years back, prominent scientists loudly announced they had actually found an exotic element functioning in nature right here on Earth. It led to one of the biggest, messiest scientific dramas of the century. I'm talking about arsenic.
Ah, yes, the monolake controversy. It serves as a perfect, albeit painful, cautionary tale for astrobiology. It highlights just how desperately we want to believe in alternative biochemistry and why we must remain fiercely, relentlessly rigorous in our chemistry.
Let's set the scene for the listener. The year is 2010. A team of NASA-funded researchers is studying Mono Lake in California. Now, Mono Lake is an extreme environment. It's a hypersaline, highly alkaline body of water that is totally toxic to almost all standard life.
Hmm.
Crucially, it is absolutely packed with naturally occurring arsenic.
Very harsh environment.
These researchers go out there and they isolate a specific extremophile bacterium from the mud, which they name GFAJ1. They take it back to the lab, deliberately starve it of phosphorus, and feed it high doses of arsenic.
Right.
And then they hold a major press conference and publish a massive paper claiming that GFAJ1 wasn't just surviving the toxic arsenic environment.
Hmm.
It was actively incorporating arsenic into the physical backbone of its DNA, literally replacing the phosphorus.
To truly understand why this announcement was so earth-shattering to the scientific community, you have to look at the periodic table again.
Okay.
Arsenic sits directly below phosphorus. It shares many of the same chemical properties and valences. But for standard Earth life, arsenic is highly toxic precisely because it looks so chemically similar to phosphorus.
It's a microscopic Trojan horse.
Exactly. Your cells accidentally absorb the arsenic, mistaking it for phosphorus. They try to use it in vital cellular energy pathways, like building ATP molecules. But the arsenic doesn't behave perfectly like phosphorus. It's slightly different size and has slightly different bond strengths.
Right.
The metabolic machinery of your cell tries to process it, jams up completely, and the cell dies.
Finding a bacterium that not only survived arsenic, but actively built its most sacred genetic code out of it was like finding a car that normally runs on gasoline, somehow running flawlessly with sand poured in the gas tank.
The biological implications were staggering, but almost immediately upon publication, structural chemists and microbiologists raised massive, glaring red flags.
Oh, yeah, I remember.
The fundamental problem lies in chemical stability, specifically hydrolysis.
This goes back to water being highly destructive, right?
Yes. If you replace the phosphorus in DNA with arsenic, you create what is called an arsenate ester bond to hold the genetic handrails together. The physical reality of the arsenic atom is that it is larger than phosphorus.
Okay.
Because it is larger, the bond it forms is physically longer, which exposes the bonding electrons to the surrounding environment. Water molecules are highly polar, and they aggressively attack exposed bonds. An arsenate ester hydrolyzes, meaning water molecules rip it apart orders of magnitude faster than a standard phosphate ester.
So DNA is supposed to be the ultra-stable, long-term archive of genetic information. It has to survive inside a water-filled cell. If you build your DNA out of arsenic, and water attacks it that easily, the DNA would literally disintegrate and snap apart almost instantly.
Exactly. The researchers who published the paper theorized that the bacteria might be utilizing highly specialized, localized environments inside the cell areas completely devoid of water to somehow stabilize the arsenic DNA.
Is that even possible?
Well, chemists were highly skeptical that such a perfect, water-free environment could exist inside a living, aquatic microbe.
The fallout was absolutely brutal. Long before traditional peer review caught up, the scientific blogosphere, I mean, this was peak 2010 internet. It just lit up.
It was a storm.
Microbiologist Rosemary Redfield publicly and systematically dismantled the paper's methodology. She pointed out terrible flaws, sloppy lab techniques, and a glaring lack of basic purification controls. Prominent science writers like Carl Zimmer heavily criticized the media hype NASA generated before the data was verified.
The scientific method ground away at the claims. Multiple independent labs around the world spent months trying to reproduce the original results, and every single one failed.
Wow.
What they eventually determined was that GFAJ1 is indeed a fascinating, highly resilient extremophile. It has evolved incredible mechanisms to survive intense arsenic toxicity. But it was not using arsenic for its DNA.
So how did it survive in the lab when they starved it of phosphorus?
It was surviving by scavenging microscopic, trace amounts of phosphate contamination present in the lab's testing salts.
No way, just contamination.
Yeah, it wasn't building an arsenic backbone. It was just incredibly, desperately efficient at finding whatever tiny parts per billion trace of phosphorus was accidentally left behind in the test tubes.
That is wild. The drama dragged on for years. The original authors dug their heels in, insisting their interpretation was correct, but science corrects itself eventually. Looking at our sources, the original 2010 paper was finally formally retracted by Science magazine in 2025, 15 long years after it caused a global sensation.
It serves as a vital historical lesson for astrobiology. First, it reinforces why independent peer review, reproducibility, and rigorous skepticism are non-negotiable pillars of science.
Absolutely.
But more deeply, it tells us why things like carbon chauvinism and phosphorus chauvinism exist in the first place. It's not always just a lack of imagination from scientists. The fundamental physical rules of thermodynamics and chemical stability are incredibly hard to break.
Right.
Life requires a profound level of molecular stability just to function day to day. Carbon and phosphorus provide that robust stability in a water environment in a way that larger, more fragile atoms like silicon and arsenic physically cannot.
That brings up a massive fundamental point. Life needs stability in a water environment.
Right.
Earth biology is utterly bound to water. But let's question that too.
Let's do it.
What if we keep carbon as our building block, but we entirely get rid of water? As we just saw with the arsenic DNA collapsing, water is great, but water is also highly destructive.
Water is arguably the most magical, unique molecule in the universe, but astrobiologists recognize it as a severe double-edged sword.
Okay, lay it out for us.
On the positive side, water has immense thermodynamic stability. It boasts a massive liquid temperature range, staying liquid for 100 degrees Celsius at Earth's atmospheric pressure. It has a phenomenally high heat capacity, meaning oceans absorb massive amounts of solar energy without boiling, which stabilizes our global planetary climate. And, highly uniquely, its solid form, ice, is less dense than its liquid form.
Which means ice floats. That sounds trivial, but if ice didn't float, life on Earth might not exist.
That's right.
If ice sank, oceans would freeze bottom up during winter. The sun couldn't melt the deep ice, and eventually the entire ocean would freeze solid into a block, killing everything. Because ice floats, it forms a protective, insulating lid on top of lakes and oceans, keeping the liquid underneath warm enough for fish and microbes to survive.
It is a miraculous quirk of physics, but water has a dark side for biology.
A distraction.
As we discussed, water actively causes hydrolysis. It is an aggressively reactive polar solvent. It constantly attacks and breaks apart large, complex organic molecules.
Right.
The greatest paradox in origin of life research is prebiotic chemistry. Getting the very first fragile, complex molecules of life to spontaneously assemble in an ancient ocean is actually incredibly difficult mathematically because the water itself constantly wants to tear them back apart into simpler pieces.
So water is constantly trying to dissolve the very life it supports. And on a planetary scale, water has another major flaw regarding climate from the sources.
Yes, the albedo effect. High albedo means high reflectivity. Water ice is highly reflective.
Okay.
During periods of global cooling, as ice caps expand, they reflect more and more solar radiation back out into deep space. This deprives the planet of heat, creating a runaway feedback loop of extreme global cooling that can plunge a planet into a snowball Earth scenario, nearly wiping out the biosphere.
So if water is this hyperactive, aggressive, climate-destabilizing solvent, what are the theoretical alternatives? Let's introduce the leading astrobiological candidate to replace water: ammonia. Our sources note this idea isn't new. It goes all the way back to a proposal by evolutionary biologist J.B.S. Haldane in 1954.
Ammonia, chemically known as NH3, is cosmically abundant across the universe, and it shares profound chemical similarities to water, H2O.
How so?
Their chemistry runs in fascinating parallel tracks. Where water can form the hydronium ion to facilitate acid-base reactions, ammonia forms the ammonium ion. Where water forms the hydroxide anion, ammonia forms the amide anion.
Wow, so there's a direct parallel?
As a solvent, ammonia is exceptional. It actually dissolves many complex organic molecules far better and more efficiently than water does.
Well, if ammonia is such a fantastic solvent and it doesn't aggressively hydrolyze and destroy molecules like water does, why aren't we swimming in ammonia oceans? Why did Earth choose water?
There are significant physical drawbacks to ammonia. The hydrogen bonds that hold ammonia molecules together are substantially weaker than the hydrogen bonds in water.
What does that mean practically for a planet?
It means its heat of vaporization is lower, it evaporates much easier, its surface tension is only about a third of water's, which makes it far less capable of utilizing the hydrophobic effect.
Remind me what that is.
The hydrophobic effect is the physical force that pushes non-polar molecules like fats and lipids together in a polar solvent. That exact force is what causes lipids to automatically assemble into protective cell membranes in water. In ammonia, building stable cell membranes becomes much harder.
Oh, that's a big problem.
Furthermore, ammonia gas is highly flammable when exposed to oxygen. This means an ammonia-based biosphere absolutely could not exist on a planet with an oxygen-rich atmosphere. We can completely rule out aerobic, oxygen-breathing life as we know it in an ammonia ocean.
But the real kicker for ammonia, the detail that blew my mind in these sources, is the temperature and pressure problem.
Right. At standard Earth atmospheric pressure, what you and I are sitting in right now, Ammonia boils and turns into a gas at minus 33 degrees Celsius.
So it's a freezing toxic gas here.
Yes. For ammonia to exist as a liquid solvent at comfortable Earth-like temperatures, say a pleasant 20 degrees Celsius, you would need a planetary atmosphere exerting a crushing pressure of around 60 atmospheres.
60 atmospheres. That's equivalent to the crushing pressure you would feel diving hundreds of meters deep underwater. So if we're looking for liquid ammonia oceans, we have to look for massive, high-pressure super-Earths, or we have to look for extremely cold worlds where the pressure is low, but the temperature is minus 50 degrees.
Exactly. And if it's a freezing cold world, the fundamental laws of thermodynamics dictate that chemical reactions will proceed incredibly slowly.
You know, I came up with an analogy for this. I like to compare these solvents to cities.
Oh, let's hear it.
Water is like New York City. It is bustling, hyperactive, highly reactive, and chaotic. Complex things get built incredibly fast, but buildings also get aggressively torn down and demolished just as fast. The energy is frantic.
I like that.
Ammonia, especially cold liquid ammonia on a frozen world, is like a sleepy, slow-moving, freezing little rural town. Delicate structures, like the first fragile prebiotic molecules of life, might have a much, much harder time finding each other and assembling in the cold. But once they finally do come together, they survive a lot longer because the slow town isn't actively trying to demolish them with hydrolysis.
That is an incredibly apt analogy for the thermodynamic trade-offs. The slower metabolic rates in a cold ammonia ocean might mean that the evolutionary journey from single cells to complex multicellular life takes tens of billions of years rather than the 4 billion it took on Earth.
Wow.
We might be looking for worlds that are far older than our own solar system to find ammonia life.
So if we are looking for a colder, slower, less chemically aggressive town than Earth, we don't even have to leave our solar system. We only need to look at Saturn's largest moon. Let's talk about Titan and the hydrocarbon solution.
Titan is, without question, the most tantalizing and fascinating astrobiological target we have locally.
It really is.
Yeah.
Here's where it gets really interesting, because when the Cassini spacecraft finally arrived and peered through Titan's thick, hazy atmosphere, it confirmed a staggering reality. Titan has a fully active liquid-based weather system. It has rain, rivers, lakes, and vast seas on its surface. But they aren't made of water.
No, not at all. The surface temperature of Titan is minus 179 degrees Celsius. The liquid in those lakes is pure liquid methane and ethane. It is literally an ocean of liquid natural gas.
Methane is a nonpolar solvent, right? It completely lacks the electrical polarity of water or ammonia.
Right, but it is vastly, wildly abundant on Titan. And this bizarre environment has birthed some of the most incredibly detailed, mathematically sound theories about methanogenic alien life.
Like Chris McKay's work.
Yes. The prominent astrobiologist Chris McKay has proposed a brilliant, rigorous thermodynamic argument for exactly what a methane-based life form on Titan might eat for energy.
Our sources outline McKay's math on this. He calculated that an alien microbe living in liquid methane could breathe in hydrogen gas from the atmosphere and consume acetylene, which is a hydrocarbon constantly produced by UV light interacting with Titan's upper atmosphere.
Yes.
The microbe would react the hydrogen and acetylene together, extract the energy to live, and exhale methane as waste. And the absolute craziest part of this story, when scientists crunched the 2010 atmospheric data beamed back from the Cassini probe, wait, actually I shouldn't trail off. When they crunched that data, it actually showed a mysterious, unexplained disappearance of hydrogen gas right at Titan's surface, and much lower levels of acetylene than their models predicted should be there.
It was an absolute bombshell finding in planetary science.
I can imagine.
The atmospheric data perfectly elegantly matched the exact chemical signature you would expect to see if a vast invisible biosphere of methane-based microbes were sitting on the surface, hungrily consuming the hydrogen and acetylene.
But is it definitely life?
Well, now, Chris McKay is a rigorously careful scientist, and he explicitly cautioned the community that this depletion could simply be the result of a purely non-biological, inorganic chemical catalyst that we just haven't discovered yet.
Oh, sure.
But even finding a non-biological catalyst operating effectively at minus 179 degrees Celsius would be a massive revolution in chemistry.
But let's assume it is life in those freezing methane lakes. What on earth is it physically made of?
Yeah.
You can't use standard Earth cell membranes.
Right.
Our biology is built on lipid bilayers, fats, that orient themselves based on water's polarity.
Right. The hydrophobic effect again?
If you dropped an Earth cell into liquid methane at minus 179 degrees, the membrane would instantly freeze solid, shatter like glass, and the cell would die.
Which brings us to one of the most brilliant pieces of theoretical synthetic biology, the azotosome.
Azotosome. What is that?
In 2015, researchers at Cornell University utilized supercomputers to model and design a hypothetical cell membrane that would remain perfectly flexible and mechanically stable in cryogenic liquid methane. They computationally tested thousands of compounds and found a winner, a molecule called acrylonitrile, which is composed of carbon, hydrogen, and nitrogen.
And wait, let me guess where we can find adrolinitriafra.
Yes. 2 years later, in 2017, astronomers pointed the massive LMA radio telescope array at Titan. They analyzed the spectral data and confirmed there are massive, substantial quantities of acrylonitrile floating high in Titan's atmosphere.
No way.
The exact hypothetical building blocks for alien cell membranes are physically present, and they are literally raining down into the methane lakes as we speak.
That feels like finding the smoking gun. But the sources do mention a debate. Just because the bricks are there doesn't mean they spontaneously build a house. There's a massive debate in the literature about whether these acrylonitrile molecules could actually self-assemble into hollow spheres in a lake that cold. Getting them to snap together requires energy.
The energetics at minus 179 degrees are undeniably sluggish. However, astrobiology is moving fast. The most recent update in our research materials, a fascinating 2025 paper by researchers Mayer and Nixon, proposes a violent mechanical solution to this assembly problem.
A violent solution.
They modeled the physical fluid dynamics of Titan's weather. They proposed that when a heavy raindrop of complex hydrocarbons falls from the sky and violently impacts the surface of a methane lake, it causes a physical splash.
Okay.
This splash exerts intense kinetic energy, forcefully pushing the layer of acrylonitrile molecules resting on the surface down into the liquid. The sheer physical kinetic trauma of the rain impact forces the hydrophobic and hydrophilic ends of the molecules to rapidly self-assemble into these protective azotosome vesicles.
The kinetic energy of alien rain violently forcing the first alien cells into existence. That is poetic.
It's a beautiful image.
And replacing water with methane fundamentally completely changes how we view genetics, too.
Mm.
The notes mention Stephen Benner's polyelectrolyte theory of the gene. I found this fascinating.
Benner is a titan in synthetic biology, and his theory highlights how water actually heavily restricts life. Because water is a strongly polar solvent, any genetic molecule trying to operate inside water, like our DNA, is forced to have a repeating, uniform, negative ionic charge all along its backbone.
Yep.
If it doesn't have that uniform charge, the molecule will either aggressively clump together or it will react destructively with the water itself. Water imposes incredibly strict, unyielding architectural limits on the shape and chemistry of DNA. But if you remove water entirely and you use a completely non-polar solvent like methane, those ionic remnants completely vanish.
The chains are off. So the architectural possibilities for how an alien organism stores its genetic data just blow wide open.
Entirely. Life evolving in methane could utilize vastly more diverse, spatially complex, and chemically unconstrained genetic structures than we could ever possibly achieve in water. Methane life might look at our DNA and consider it an incredibly primitive, restrictive, basic way to store data.
Okay, we've thoroughly explored freezing cold methane on Titan. Let's swing the pendulum to the absolute opposite extreme. Let's talk about hot, pressurized, truly bizarre solvents. What about our planetary evil twin, Venus?
Venus is the quintessential planetary hellscape. The surface temperature averages 470 degrees Celsius, hot enough to melt lead. The atmospheric pressure is 90 times that of Earth, equivalent to being a mile underwater.
That's brutal.
But if you look high up in its atmosphere, around 50 kilometers off the surface, the temperature and pressure drop to Earth-like levels. And floating in those clouds are massive droplets of concentrated sulfuric acid.
Sulfuric acid is terrifying. It strips flesh from bone, it violently dehydrates and destroys organic matter.
To standard Earth life, it is an instant death sentence, yes. But chemically speaking, sulfuric acid is an incredibly potent, strongly polar solvent. It actually remains a stable liquid across a massive temperature range, far wider than water, remaining liquid up to 337 degrees Celsius. Yes. And a highly respected committee from the National Research Council formally theorized that a totally alien biochemistry could theoretically exist within that acid, provided it utilized different fundamental chemical bonds.
Like what?
For example, where Earth life constantly relies on the carbon-oxygen double bond, the carbonyl group, a Venusian life form evolving in acid, could substitute the carbon double bond, the alkene group, to function identically without being destroyed by the acidic environment.
The adaptability of chemistry is staggering. What about Carl Sagan's wild idea regarding hydrogen fluoride?
Hydrogen fluoride is an incredibly potent, fascinating polar solvent. It is a massive dielectric constant. It can seamlessly dissolve complex paraffin waxes, which water absolutely cannot touch. It forms strong hydrogen bonds, much like water.
So what's the catch?
The fatal flaw for HF is cosmic abundance. Fluorine is a remarkably rare element in the universe compared to oxygen, carbon, or nitrogen. Synthesizing enough fluorine to fill a planetary ocean is cosmically highly improbable, making HF oceans an extremely unlikely candidate for life.
Our sources also highlight Dirk Schulze-Nakuch's theories on hydrogen sulfide, specifically looking at Jupiter's moon, Io. Now, Io is the most violently volcanically active body in the entire solar system. It is constantly erupting sulfur.
Hydrogen sulfide is a direct chemical cousin to water sulfur, sits right below oxygen on the periodic table, but it is much less polar and is a significantly weaker solvent. It only manages to stay liquid over a very narrow temperature range.
Okay.
However, under immense pressure, perhaps trapped in deep subterranean pockets beneath Io's volcanic surface, it could theoretically act as a solvent. Schulze-Nakuch hypothesized a life form there that might use carbon monoxide as its primary carbon source and actually breathe sulfur monoxide instead of oxygen to survive.
But my absolute favorite extreme solvent detailed in the notes is supercritical fluids, specifically supercritical carbon dioxide. Feels like magic.
It does border on the surreal.
Yeah.
When you take a gas like carbon dioxide and subject it to immense crushing temperature and pressure, it crosses a physical threshold and enters a supercritical state.
What does that mean?
In this state, it ceases to be just a gas or just a liquid. It behaves like both simultaneously. It can effuse and expand through solid materials like a gas, but it can aggressively dissolve complex materials like a heavy liquid solvent.
Where would we find entire oceans of this stuff?
On dense super-Earth or super-Venus exoplanets, massive rocky worlds with incredibly thick, high-pressure atmospheres could generate global oceans of supercritical CO2 near their surfaces.
Wow.
And lab tests show that supercritical CO2 is a phenomenal solvent. It selectively dissolves complex organic compounds beautifully while leaving others intact, which is exactly the kind of selective chemistry life requires to build cell walls and complex proteins. It could easily, robustly sustain a totally alien biochemistry that would vaporize instantly if brought to Earth.
Learning about all these extreme, pressurized, toxic environments raises a massive question for me. If biology can somehow adapt to these bizarre extremes, could life completely change its active state depending on how hostile the environment gets? Like, if an environment fluctuates from habitable to deadly, could the alien life just switch itself off until things improve?
It absolutely could, and astrobiologists refer to this as adaptation to variable environments. We don't even have to look to aliens to see this. We can look at Earth. Consider the desert-dwelling frogs in the arid regions of Australia.
I've heard of these.
When the dry season hits and water vanishes, they don't die. They burrow deep underground, encase themselves in a cocoon of shed skin, and actively dehydrate their bodies by up to 75%.
75%.
They enter a state of extreme suspended animation, slowing their metabolism to near zero, and they wait, sometimes for years, until the rains finally return.
So if a frog can do that, an alien extremophile could take it to the extreme.
Exactly. If we extrapolate that evolutionary mechanism to a hostile, fluctuating alien planet, you could easily have microscopic life forms that hibernate for centuries, or even millennia, during brutal, freezing planetary winters or periods of intense radiation.
So they look dead to us.
If one of our robotic probes landed during that hibernation period, scooped them up and analyzed them, they would appear completely, utterly biochemically dead. We would catalog the planet as lifeless, entirely missing the fact that the biosphere is merely asleep, waiting for the planetary climate to shift back into its habitable zone.
Okay. We have pushed biological chemistry to its absolute breaking point. We've swapped the solvent from water to methane to acid. We've changed the genetic backbone. We've swapped out the carbon atoms. We've flipped the chirality. But what if we just throw out chemistry entirely?
This is the wildest part.
What if life doesn't actually need chemistry at all? What if it just needs physics?
Now we are leaving the comforting realm of planetary biology entirely, and we are entering the mind-bending realm of theoretical astrophysics. We are talking about the concept of non-planetary life.
The sources cite a fascinating 2007 paper by physicist Vadim Sitovich regarding dusty plasma life. What exactly is dusty plasma?
Plasma is the fourth state of matter. When you heat a gas to immense temperatures, the electrons are ripped away from their atoms, creating a superheated, highly ionized cloud. Plasma is what makes up stars, lightning bolts, and the vast empty stretches of interstellar space.
Okay.
Zatovich utilized highly complex supercomputer models to simulate what happens when microscopic inorganic dust particles are suspended inside a plasma field. He found that under the right electromagnetic conditions, the dust doesn't just float randomly. It becomes highly charged and spontaneously begins to self-organize
But organized into what? Are we talking about basic geometric shapes or something more complex?
into highly complex, microscopic, reproducing helical structures. The dust particles align themselves into spiraling strands. Because of the complex electromagnetic forces in the plasma, these strands attract each other.
They interact.
They interact, they pass structural information back and forth, and most astoundingly, they undergo spontaneous structural bifurcations. To put it simply, they divide. They split into two identical copies. Mathematically and physically, their behavior is nearly indistinguishable from biological cellular division.
But there is no carbon. There is no water. There's no DNA.
None. It is an entirely inorganic, non-chemical system exhibiting the fundamental lifelike behaviors of replication and information transfer driven purely by electromagnetism and plasma physics.
That is dust floating in the vacuum of space. But what about the extreme opposite? What about inside the crushing nuclear furnace of the stars themselves? There is a 2020 hypothesis detailed in our notes by physicists Enkerdokwi and Chudnovsky that sounds like pure, unadulterated magic. They call it cosmic necklaces.
It is deeply, intensely theoretical, but it is entirely mathematically sound within the framework of modern string theory. The physicists propose that deep inside the core of a star, amidst the nuclear fusion, you could have entities known as magnetic monopoles.
Monopoles?
Hypothetical particles that possess only a single magnetic pole, either a north or south, but not both. These monopoles could be tethered together by one-dimensional cosmic strings, which are theoretical fractures in the fabric of space-time itself left over from the Big Bang.
So you have a string connecting these magnetic particles. How does they become life?
The intense, chaotic nuclear forces and the immense crushing gravity of the star stretch and twist these cosmic strings into highly complex, incredibly stable, tangled configurations.
The physics paper literally states that these strings stretch into complex DNA-like forms.
Yes. The specific twists and knots in the string can act as stored information, just like the sequence of A, T, C, and G on DNA. And over billions of years, driven by the ceaseless thermodynamic churn of the star's nuclear core, these string structures could theoretically mutate, replicate, and undergo a bizarre form of stellar Darwinian evolution.
I have to stop and wrap my head around this.
Yeah.
Let's say this stellar string theory life evolves, and let's say over billions of years it actually gets smart. It becomes an intelligent, star-dwelling civilization.
Yeah.
How would humanity ever know? We can't land a Mars rover on the surface of a star. We can't scoop up stellar plasma to sequence it.
The implication for observational astronomy is absolutely staggering. If a highly complex, intelligent string theory civilization evolves inside a star, it would eventually run into the same problem every civilization faces. It needs energy to sustain its growing complexity.
Right.
It would naturally start harnessing the star's own internal nuclear fusion energy for its own survival. If it begins actively consuming and directing that massive energy, the outward thermodynamic output of the star would change.
So we could see that change.
To our telescopes, the star would begin to cool down significantly faster or look mysteriously dimmer than our standard cosmological models predict it naturally should.
Oh my God. So if an astronomer looks through a telescope and sees a distant star dimming mysteriously or fluctuating wildly, well, it might not just be an alien megastructure like a Dyson sphere built out of metal around the star. The star itself might be infected with intelligent string theory life that is actively eating the fusion core from the inside out.
That is precisely the hypothesis, and it brilliantly affirms exactly what we've been attempting to do on this entire deep dive. It pushes the very definition of life completely out of the restrictive confines of biology, entirely past the rules of chemistry, and directly into the realm of pure, fundamental structural physics.
Wow.
It argues that life is simply localized information processing and replication by any means necessary, using whatever materials the universe provides.
That is, wow. Okay, we need to ground this back down to Earth. We've covered mirror microbes, liquid methane oceans, and stellar plasma strings. So what does this massive stack of information actually mean for you, the listener? Why should you care about hypothetical biochemistry?
It's a great question.
Learning about this isn't just about trying to predict what aliens might look like in the next big science fiction blockbuster. It is deeply about understanding us. When you see how many other incredible, bizarre, complex ways life could theoretically work, it forces you to understand how truly special, how incredibly fragile, and how incredibly specific Earth's carbon-water system really is.
Yes.
It thoroughly cures us of our carbon chauvinism. It shows us
Yes.
that human biology is just one beautiful, specific melody in a universe capable of playing infinite potential instruments.
It vastly expands the boundaries of our search for life in the cosmos, but it also brilliantly highlights the precious, fragile contingency of our own existence here on Earth. But I want to leave you with one final, deeply provocative thought to ponder.
Okay, what is it?
We started this journey by talking about the shadow biosphere, the highly plausible idea of vastly different, extreme surviving microbes hiding right here on Earth, deep within the crust. Microbes, perhaps made of mere DNA, entirely invisible to our immune systems, silently sharing our planet for billions of years deep underground.
Right. It's a terrifying, fascinating prospect.
Now, think about what humanity is aggressively doing right now in the 21st century. As we frantically transition away from fossil fuels to save our climate, we are increasingly relying on deep, enhanced geothermal drilling for green energy.
Oh, wow.
We are engineering machines to fracture bedrock miles beneath the surface, pumping down superheated fluids and bringing deep, ancient crust materials violently up into our surface biosphere. Could our desperate, well-intentioned attempts to save our own fragile carbon-based biosphere accidentally awaken or expose us to a parallel alien biology?
That is,
If we drag up a shadow biosphere that our immune systems are entirely blind to, we might realize too late that we are digging into the profound unknown just to save the known.
we might just find out that the aliens have been waiting patiently beneath our feet this entire time. Thank you so much for joining us on this deep dive. Stay curious, keep questioning the baseline, and remember, your entire reality might just be a localized bias.